Right, so this video is going to cover ionization energies. It's a fairly, it's a reasonably small topic, but it's one that almost always comes up on papers, and it can often have a question just solely on ionization energies, which is quite a good one to get marks on because actually it's quite straightforward. So first thing, ionization energy. What does that mean? Well, there's a definition for this, and it's a definition that you must learn, and it is as follows. It is the energy required to remove one electron from each atom in 1 mole of gaseous atoms to form 1 mole of gaseous ions. So that's your definition. Now, there's obviously, within the whole of the Unit 1 and Unit 2, there are a few definitions to learn, and you've got to make sure that you can do them. You can absolutely nail them. This might be worth a couple of marks, and actually if you can just sort of regurgitate that onto a page, that's 2 easy marks out of 70 for your Unit 1, and that, that could be the difference between, your C and your B, or your B and your A. So it's important to have your definitions down, because there's no excuse for not getting those marks. Application questions, yeah. Stating stuff, recalling things, there's no excuse. So what does this actually mean? Well, as it says, it's the energy required to remove an electron from each atom in 1 mole of gaseous atoms to form 1 mole of gaseous ions. So in reality, it would look something like this. So if I take a mole of oxygen atoms, no atoms, I'm not doing O2 here. Okay, we are not dealing with O2. It's purely atoms. Okay, so regardless whether they're diatomic or what they are, we're just dealing with single atoms. Key thing, make sure you include the state symbols, because the definition does state gaseous, therefore you must have that there. You haven't got the G, you're not going to get the mark, unfortunately. So going across, we're going to produce then 1 mole of gaseous, again the G, ions, and an electron there. So 1 mole of atoms gives us 1 mole of ions and 1 mole of electrons as well. Now we don't have to worry about the numbers of electrons really. We can ignore that. You can include that in the definition. There are a few different variations of this, but ultimately, it could be the energy required to move a mole of electrons from a mole of gaseous atoms, etc. There are a few variations. I like this one. It makes sense to me. So this is oxygen. Just to give you another one, magnesium, for example, then would be Mg gas goes to Mg plus gas plus electrons. Now these are both classed as the first ionization energy. I'm going to abbreviate that to IE. So these are the first ionization energy, and what that means, it is the energy value associated with this would be to remove 1 electron from there. So our second ionization energy, if we were asked to write an equation to show that, it would be as follows. So it would be an O plus this time, G going to O2 plus, G plus electron. On the other hand, the magnesium would be Mg plus going to Mg2 plus plus electrons. So still the same thing we got there. We've got the gaseous parts and we've got the correct charges and electrons. Note though that we do not start with atoms here for our second. We start with ions, and that's because this is the second ionization energy, and therefore the definition changes. It's not going to be the same as the first one. This would be the energy required to remove 1 electron from each ion, each unipositive or singly positive ion in 1 mole of gaseous ions, or gaseous unipositive ions, to form 1 mole of gaseous 2 plus ions. So you've got to include the charges into them. This is the second ionization energy. Now you could be asked for the fourth ionization energy, for example, and I've come up with a fantastic way of remembering this, and that is that the number of the ionization energy they ask for, that will equate to the charge of the ion produced. So my fourth ionization energy, for example, fourth ionization energy of chlorine, I'm going to be producing the Cl 4 plus ion, stick in my gaseous, stick in my electron, and therefore I must start with the 3 plus. Okay, so if you ever get confused with that, don't have to worry about counting up. This number here, second or fourth or first, is going to equate to the charge of the ion produced. That's the key thing, charge of the ion produced. Just bear that in mind. It's one that they could ask you varieties of these. Okay, so that's how you would write out that, and that comes up very often. They love to ask that because it's a very easy one to get sort of a mark out of. Probably not going to get 2 marks, or you might do 1 for charge, 1 for gaseous parts. Oh, error there. Okay, so the next thing they like to do, they like to talk about various trends and factors that change your ionization energy. There are really 3 factors that will affect the ionization energy, and they are as follows. We have the charge of the nucleus, we have the distance from the nucleus, and finally, you may have guessed it, we're going to have shielding. So these 3 things affect the ionization energy, and they do so because of the following. And what I'll do is I'll show you a sodium atom in an old school electron configuration. So this is a sodium atom. This is my sodium atom right here. If we look at this as an individual example, this electron right up here, this would be the one that's removed as my first ionization energy. So that's going to be the first ionization energy. Then any of these is going to be our second, followed by third, fourth, fifth, sixth, seventh, eighth, ninth, then going down here 10th and 11th. So first is always going to be that one of those outer shells. So we start with the outer and we work in. So the opposite of sort of how we fill, we do the opposite working backwards. And you could do that. You could look at that from the other point of view of the A level way of writing this out. So for a sodium atom, 1s2, 2s2, 2p6, 3s1, we're removing the 3s, then we're moving the 2p, then the 2s, and then the 1s. So we're going in that order, completely backwards. What you can see here is for any atom, when it says charge of the nucleus, the charge of the nucleus dictates sort of the attractive force between these outer electrons and the nucleus. So the stronger the charge of the nucleus, the stronger this force will be. Therefore, the more tightly this is held, the more difficult it is to remove it. Therefore, the ionization energy would be greater. So, increase charge, increase ionization energy. And that hopefully makes sense. It's held more tightly, therefore we've got to put more energy in to actually rip it away. Distance from nucleus, it's a similar idea. If we look at this one here, compared to this one here, this electron, if we were to have removed all these already, this one is being removed from it's being removed from much closer to the nucleus. Therefore, there's much more attraction there. This one's much further away, so there's less attractions. This one would require much more energy compared to this one. So again, this time we could say increase distance, decrease ionization energy. And finally, the shielding one. Well, it's similar to this distance one, really, because distance and shielding go hand in hand. So this one, although it's further away, also has some shielding from this shell. This one has further away, but also has shielding there. So same as the distance, increase in shielding, it leads to a decrease in ionization energy. One other point worth sort of talking about here is that factors affecting ionization energy. Every time you remove an electron, you create a positive ion. Now, when you have to remove that next electron, you're removing it from a positive ion or a more positive ion, which means that it's going to require more energy. So charge and nucleus, you could also sort of say charge of ion, really. And we'll go charge of atom / ion. So charge of an atom is 0. Therefore, to remove this would be a value. As once we've removed that, we're going to have a positive ion. Then when we remove the second electron, we're removing it from a positive ion. Therefore, this electron is more strongly attracted. It's stuck here more tightly. So we've got to put more energy in to remove it, and so on as we remove all of the consecutive electrons there. So there are factors involving the ionisation energy. And what they like to do is they might give you two examples. They might give you sodium and potassium and give you their values of ionisation energies, first ionisation energies, and ask you why the values are different. At which point you would talk about, in that case, charge the nucleus isn't going to have as much of an effect. That's mostly when we're talking across the period. These two are going to be down the group. So for example, sodium and potassium, sodium being here, potassium being below it, with lithium above sodium. So we're looking at these two. Sodium is going to be a smaller atom. Therefore, because it's smaller, this is opposite, so we've got less distance, therefore greater ionisation energy. This one's going to be bigger, therefore it's going to be easier to remove that. So down the group, ionisation energy is going to decrease, as opposed to across the period, it's going to increase. And the main reason for that is down the group, atom size is increasing, distance from nucleus, blah, 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 blah. Across the period, the actual distance is getting smaller, and that's also paired with the fact that the nuclear charge is getting greater and the shielding is remaining equal. So that's a point to be aware of. And actually the trend in the period, particularly period 3, is covered in another video, the periodicity video, so I'm not going to talk too much about that there, but I will actually show you now a graph of what it looks like down the group, just to give you an idea actually how that does change. So I'll just stick that here. So what we can see here is, obviously this is down group 1. Lithium is going to be our smallest atom, and for this is going to be our biggest down here at potassium. And the trend is actually true. The enthalpy change, this is the this is actual ionisation energy in kilojoules per mole. That has decreased, as I said it would, and the reason there is because you can see that we've got an increase in shielding. We've got increase in distance, and although there is also an increase in nuclear charge, it's counteracted by these two changes. So there you go, distance increasing, and we can see therefore, as obviously with the shielding as well, the ionisation energy is decreasing. Now a couple of other points here. This point I want to look at what happens really with sort of also the consecutive ionisation energies of elements. So look at sodium first of all. So here we have a graph of sodium's ionisation energy. So you can see here the ionisation energy number going from 1 through to 11, and this is corresponding to our sodium being 1s2, 2s2, 2p6, 3s1. So our 11 electrons there. And what we're doing is we're moving this in backwards. So this is our 3s1. This is going to be 2p6, 2p5, p4, p3, p2, p1, s2, s1, and actually we'll keep these numbers in. And finally 1s2 and 1s1. So what you can see is a definitive change, and I've used a logarithmic scale to try and make this a little bit more clear. It does help with this slightly, otherwise you don't see this difference, very clearly, particularly because of the massive change up here. What we see is very clearly there's this change, and the change is that this first one's down here, relatively low, so around 700-ish. When we remove that, we have a big jump up to here, up to this point here, and then we go fairly steadily increasing. As I said before, we're moving from a more positive ion each time, blah 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 blah, getting greater and greater, and then we have another jump up here. Now the reason for that is that we're actually changing energy level, and that's the distance coming in here. So we're going from furthest away to closest up here, and that makes that much difference, and you can see this clear jump here. And we can see that again if we were to look at magnesium. So the same is true here. We can see that we have, again, I'm not going to worry putting the actual electrons in, but what we've got is we've got third energy shell here, second here, and first here. So we've got closest to the nucleus, this is, closest to the nucleus, and furthest away from the nucleus. And we can see that same pattern. Every time our consecutive one is always increasing, but it increases, then a big jump, increases, 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 big jumps. Every time we move into the next energy level, the next energy level down, we have a big jump. And what's quite good is this actually means that we can use this idea to actually identify elements to an extent. So if we were told what period an element is and we were given a graph like this, we could actually decide what the element was, or if we were given the numbers in a table, we could see what the element was. So it might look something like this. So here we've been given a graph here, or we could have been given these as values, but it doesn't matter. But what we've got is we've got 4 values increasing, big jump, big jump. You can see we're going from about 6,000-ish around here, so 6,000, around about 6,000, up to what, 37,500, something like that. So we've got a massive jump up between there, massive jump, which to me instantly tells me that, well, that means I must be moving into a different energy level. So if I'm removing 4 and then I'm jumping, there must be 4 electrons in this outer shell. So I'm looking for an element with 4 electrons in the outer shell. Now, I would be told in the question that this is a period 2 element, and I'm asked then to, what's the identity of the element? So I'm in period 2, I've got 4 electrons in the outer shell, and just to sort of reiterate how I got that point, so I'm removing 1, 2, 3, 4. Not much of an increase. There is an increase, but it's a steady increase as I'd expect. This jump tells me I'm moving to a different energy level. Now, because these are all 6 of them, we've got 6 electrons here. We've got a big jump between this fourth electron and the 5th electron being removed there, which tells me I'm moving from an outer shell into an inner shell. Means that actually this, in the old school way of looking at it, this must have an electron configuration of 2, 4. So we can see 2 here, closest in, and 4 on the outer. Well, this must be carbon. And if we look at carbon, the ionization energy of carbon is 1s2, 2s2, 2p2. And that fits perfectly. We're removing 2p2, 2p1, 2s2, and the 2s1, and then we jump into that next energy level, and there's our 1s2 and our 1s1, and that's a big difference, and you can see that huge increase in energy required to remove that electron versus this one. The other one that they quite like in exams is this one, and when I say they quite like it, it's come up once, so it's not really as common as certainly the others are. Spot the element, that's this one down here, spot the element, that has come up a few times in the last few years, so make sure you can do that. This one less so, but I quite like this anyway because it's playing with trends. So it says, use your understanding of electron arrangement to complete the table by suggesting a value for the third ionization energy of magnesium. Now magnesium is 1s2, 2s2, 2p6, 3s2. Now we know it has 2 electrons in this outer shell, this third shell here. Then it has 8 in the next one and 2 in the final one. So that means these 2 are going to be increasing. Then we know we're going to have a big jump to this one here. Big jump. Which means this should be in line with these 2. Which would be, basically this is going to be your 3s2. This is going to be your 3s1. This is going to be the 2p6, 2p5 and 2p4. So these we would expect a general trend again. Keep going and then there'll be another jump. So big jump between this and this. In order to work this out, you actually can ignore these. Doesn't matter. It's these we were looking at. And we say, well, what's the difference between these? The difference between these is 1629 minus 10,500, which is roughly what? 3,100-ish? Yeah, 3,129. So we've got 3,129 going from there to there. So the way we work this out, we'll just take 3,129 off that, and that gives us a value of 7371 from just working that out now. Now in the exam situation they were very, very generous, and actually the answer, they were allowing anything from 5,000 to 9,000, which I think is a little generous, and the actual value, the real value actually, if you look it up, is 7771. 732.7. And you can see just by following this trend, we actually get remarkably close to that. We're 400 away, but that's pretty close considering we've just basically looked at a trend and worked that out. And there you go. So 7371, bang in the middle almost of that. That's absolutely spot on. That's a perfect answer there. That actually is it. That's it for ionisation energies, really. So hopefully that has been of some help. And if these kind of questions come up, then hopefully you are prepared for them. Again, any comments or requests or anything, stick them in the comments. And I hope that's been of some help.